In this video, we will discuss Monte Carlo Simulation, which is a branch of computational algorithms that use probability distributions to complete optimization on a relatively undefined or overdefined problem. Recall the video on deterministic and stochastic optimization. There, we discussed that you would use stochastic optimization when there is just way too much unaccounted for, or too much to account for. In these instances, developing and solving the optimization problem analytically becomes very difficult, or even impossible, so we move from deterministic to stochastic optimization. To begin the process of Monte Carlo simulation as part of stochastic optimization, let us say that every single range of our parameter values could be described by a random variable encompassing all values within that range. Next, we use the central limit theorem, which states that random variables that are independent of each other and identically distributed can be approximated using a normal distribution. Independent and identically distributed means that each random variable does not have any dependence on other variables, and that each value that the random variable could take on is distributed equally from each other. Now that we have successfully created normal probability distributions from our random variables, we can use a random number generator endemic to the software we are working with to randomly sample values out of our normal distributions. With this, we can generate a sample of the many different designs from the solution space. Using our metrics for product validation, we can either pick out the best design, or get an indication of where the most optimal designs are and iterate forward with the new parameter ranges. An example of optimization using Monte Carlo simulation is the calculation of the irrational number pi using a circumscribed circle within a square. Each side of the square lies tangent to the circle in each cardinal direction, like so. Given that the diameter d of the circle is 2 times the circle radius, or 2r, we know using geometry that the area of the square is 4r squared and that the area of the circle is pi r squared. But, what does pi equal exactly? To calculate pi, you take a sample of random values within the square. Next, you divide the number of points inside the circle by the total number of points inside the overall square. Finally, you multiply the quotient by 4 to isolate the value of pi. This process is analogous to design optimization in the way that improving the estimate of pi is the design we want to optimize, and the restrictions placed by the square and circle geometries and relationships are our constraints on parameter values. As we run the Monte Carlo simulation with an increasing number of points, we still find that even with so many points used, our estimation of pi is still not totally accurate. By the central limit theorem, as the number of points we sample approach infinity, we should get a mean of around the actual value of pi for our solution. But as with computer-aided engineering, we face the law of diminishing returns. For a much more complicated problem than this one, each iteration might take a long time, meaning that finding any good solution would be computationally expensive. As a result, Monte Carlo simulations are also used in circumstances when there is no way to find an analytical solution or when finding an analytical solution would be even more computationally expensive. Thank you for watching this video. See you in the next video.